You.
Okay, welcome everybody to April General.
Kmart shoppers.
Quiet!
Thank you. Thanks for coming for the April General meeting with LDAS. We're really happy tonight to have Dave Spiegel here to present with us. He's a leading worker in exoplanet discovery work, and so I'm really excited. Now, I think there's probably only one member that can understand this on Dave's level, and that would be Joshua Pepper. And I don't think I've seen him here tonight. So think of us as like undergrads, maybe, and we'll take it from there. But and I really have to apologize today. Between Lloyd and myself, we sort of dropped the ball, and he came up here not even knowing for sure if he was presenting tonight. But he's been a real pro, and please welcome Dave Spiegel.
Hello, so thank you for the introduction. And actually, the talk that I'm going to give you is very similar to the talk that I give to general professional audiences as well. And I think that's not a mistake. I think you guys will be able to follow and hopefully enjoy it. Some people might not like being interrupted when they're talking, but I'm not one of those people. If I say anything that's unclear, if you have questions, please feel free to shout out. It's a little dark in here, so I might not see if you raise your hand. So feel free to just speak up. So there are several topics that I was hoping to cover today. Exoplanets, astrobiology. Astrobiology means different things to different people, but I mean basically the search for life in the universe. And time permitting, I might say something about the long-term evolution of planetary systems. I'm going to start off with, so I guess I should also give you a little more of an introduction to myself. I got my PhD at Columbia University a few years ago, working with Kristen Manu and Caleb Scharf. Caleb Scharf has written probably the best textbook on astrobiology at a college level. If you're interested in kind of getting started in exoplanets and astrobiology, I strongly recommend Caleb Scharf's textbook. I then moved on to Princeton University and did a postdoctoral fellowship there for 3 years, and then I made the long move across town from Princeton University to the Institute for Advanced Study, where I've been for the last 3 years. And it's a wonderful place to work. I feel really privileged to have been there. And I'm happy to be here tonight. I'm really glad that people showed up. It's a really fun topic. It's what got me interested in astronomy in the first place, and I hope you all share my enthusiasm for it. I also should start off by saying thank you to the Friends of the Institute and the Keck Fellowship, which has made my term at the IAS possible. So I'm going to start with a quick little quiz where I'd like all of you to think of the answer to the quiz in your mind, but don't shout it out. Here it is. Imagine a test for a disease that's a really accurate test. 99% sensitivity. And what sensitivity means in disease testing lingo is that the probability that the test gives a positive result, given that the patient is sick, is 99%. It's 99% sensitive. And it's 99% specific. The specificity is the probability that the test gives a negative result, given that the patient is healthy. And that's also 99% for this test. And so the quiz is, and again, don't shout out the answer, if a patient goes in and gets tested and gets a positive result on the test, how nervous should she be? What's the probability that she's sick? I'll come back to this in a moment. But before, I'd like to give you a tour of an exoplanetary system. This here is a three-dimensional, or it's a visualization of a part of a three-dimensional model of a hot Jupiter that I put together with some colleagues whose names are cut off here. Adam Burrows, Emily Rauscher, Kristen Manu. This is the planet HD 209458b. It's a kind of boring name, but it was the first planet that was seen to transit across the face of its star from Earth's perspective. I'll return to what that means in a moment, but it's one of the two methods that's found most of the known exoplanets. And what we're looking at here is two different isopressure levels, so two different levels of constant pressure in the atmosphere. The color, it indicates the temperature. And these two levels in the atmosphere, the deeper one is at 3 bars. That's 3 times the pressure here in this room. And the one farther out is at 1/10 of a millibar. So roughly 1/10,000th the pressure here in this room. And there are many things to say about this. I'm only going to say a few. You can see that deeper in, the temperature is more homogeneous from day to night. But there's a difference from the equator to the pole. The equator is warmer and the pole is cooler. Whereas at higher altitude, there's a strong day-night asymmetry where the day side is really hot and the night side is comparatively cool. There's a lot of other stuff going on. There's circumpolar vortices, winds going around the planet at the deeper level, whereas at the higher level, the winds more go from the day side rushing around to the night, not in a circulation pattern, but rather directly taking the shortest path to the night side up at high altitude. This is all a model, so it might not actually represent what's going on the real planet, but it represents most of what we know about the planet, together with our best implementation of the laws of hydrodynamics and radiative transfer, given this circumstance. Now, one of the reasons I like this so much is that this basically is a picture of a planetary system around another star. And you might say, well, it's not really a picture. It's a picture that I made in a computer. It's not really a picture of the planetary system. But what I'd like to convince you is that that's sort of a difference in degree, but not in kind, from any picture we ever have, whether with our eyes, with our iPhone camera. What this is a model that's constrained by data. And the amount of data that's constraining this model is fairly small at this point. In the future, as time goes on, the amount of data constraining the model will increase, and the range of models consistent with the available data will decrease, and we'll have a more and more specific idea of what is actually going on this planet. But if you pull out your iPhone and you snap a picture, that also doesn't take a picture of what's actually there. It records electrons in different locations on a sensor. And the electrons that are recorded then have to be interpreted via a model to put together a picture that you see on your computer. Or even with your eyes. This is a picture that I made, so I know exactly what's going on here. How many colors do you see here?
Many.
Good answer. 4. People often say 4, and there might be something to do with how far away you are, but there's people often see an orange color, a purplish color, a bluish color, and a greenish color. And I made this picture, and when I look at it, I still see purple, orange, blue, and green. However, those who said 3 were actually right. There's a purple, an orange, and sort of a blue-green color. The blue-green color really looks like green to me here and blue to me here. But it's just a single color. And so what I'm trying to show you here is that even when you look with your eyes, you don't see what's really there. Right? There's some data, and it's constraining some model that your brain has that tries to interpret the light that you take in and form a picture of the world from that. But it does it imperfectly. So what we're doing in terms of putting together this movie, what I'm doing here, yeah, there are way more actual possible planets that are consistent with the known data than I'm showing you right here. But this is sort of a philosophical point. It's not so different in principle from what happens with your iPhone camera or even your eyes when you look at something. And again, as time goes on, we're going to get a better and better idea of what these planets look like. So the overview is that I'll talk briefly about what factors influence climatic habitability. I'll talk about what are the astrobiological implications of the fact that life emerged on Earth fairly early after the young Earth became habitable. And finally, time permitting, I might say a few words about what happens to a solar system when the star grows old. And the conclusions, which I'll get to over the course of the talk, but I'll tell you at the beginning, the conclusions are that it's an exciting time to study exoplanets. Dynamical interactions between planets can affect long-term habitability. The time when life arose on Earth does not place strong constraints on the probability of life arising elsewhere. And the evolution of systems when stars grow old leads to two populations of companions to white dwarfs. And it can also alter any planets that might be nearby. So, astrobiology or exobiology are words that are fairly young, but the ideas, of course, are much older. This is a globe made from the maps that Percival Lowell put together from looking at Mars. This is from 1906. So most of you are probably familiar with this, that Percival Lowell used to look up at Mars, thought he saw these linear features that he interpreted as canals and irrigation ditches built by a dying civilization to bring melting water from the polar caps to the parched midlands, everywhere else they needed the water to be. Of course, this is what Mars actually looks like as seen by the Hubble Space Telescope. And although this bears some similarity to Lowell's map, it doesn't have all those canals that he thought he saw. Going farther into the past, in 1695, Christian Huygens finished writing his treatise Cosmotheoros, which was subtitled in translation, New Conjectures Concerning the Planetary Worlds, Their Inhabitants, and Productions. And in it, he pointed out that the moon and the other planets in our solar system are not so different from the Earth and probably have their own inhabitants, plants and animals, just like the Earth. He also pointed out that the other stars in the sky are probably not very different from the sun and probably have their own planets and moons with plants and animals on them. And he even noted that Jupiter and Saturn are far enough from the sun that water would be in its frozen form there. But of course they have inhabitants, according to him, who would need water. So he said they must have a different kind of water with a lower freezing point. And he was kind of right if you think about methane or ammonia, but if you think about actual water, he was wrong. So this slide is sort of a cautionary tale of ways that both observers and theorists can be led astray by hope in ways that probably still to some extent happen. Hopefully the rest of this talk is not contaminated with that sort of problem. Exoplanets are a fairly recent discovery, but I looked back in the astronomical literature, and the first claim I was able to find of the detection of a planet around another star was actually made in 1855 by a fellow who published under the name Captain W.S. Jacob. Now, he was looking at this binary star system, 70 Ophiuchi, and he thought that he saw one member of this binary star doing a little wobbly motion in the sky, which he interpreted as being due to the gravitational influence of an unseen companion, the planetary companion that he claimed he saw. And subsequent observations have ruled out the kind of planetary companion that he thought he saw. Over the next 130 years, there were more than a dozen claimed discoveries of exoplanets, mostly through this same method, which is called astrometric wobble. Astrometry is noticing exactly where, or measuring exactly where something appears to be in the sky. So if something appears to move in the sky, that's astrometric wobble. Until the first actual detection of an exoplanet it's typically credited as being in either 1991 or 1995, but the real first discovery was in 1988 around Gamma Cephei by Bruce Campbell and collaborators. The reason this one often doesn't get credit for being the first is that Gamma Cephei is a somewhat active star, and alternate explanations for the signal that they saw weren't ruled out for another 15 years. But it turns out that the signal they saw really was due to a planet, and that was the first one. And there was another actually in the same year, led by Dave Latham. So transits are, as I mentioned, when a planet crosses the line of sight between us and the parent star. And transiting planets, when the planet transits in front of the star, we don't see a little black dot crossing a stellar disk, because the stellar disk appears like a point to us. What we do see is that the light from the star gets a little bit dimmer. So if Jupiter, for example, were to transit across the face of the sun from the perspective of an alien civilization that was right in Jupiter's orbital plane, it would cause about a 1% dip. Earth would cause about a 0.01% dip, 1 part in 10,000, which is a really slight dip, but it's actually measurable. And we've measured Earth-sized planets transiting sun-like stars. Interestingly, the transit method of detecting exoplanets was first suggested by Otto Struve in 1952 and fleshed out by his collaborator Su-Shu Huang in 1959. This is something that most astronomers are unaware of, because transiting exoplanets weren't first seen until the year 2000. And that's basically because nobody was looking. So, in fairness, it would have been really hard to see 1% dips back in the 1950s. But with a dedicated search, it might not have been impossible. The reason why nobody looked was because nobody thought that Jupiter-sized planets could be in really close to their star. People thought that other solar systems were structured basically like our own, with Jupiter-sized planets at Jupiter-like distances. So 5 astronomical units, 5 times as far as the Earth is from the sun, is where Jupiter is found. And out at that distance, the a priori probability that the planet would ever transit from our perspective is 0.1%, and the transit would last about 1 day every decade. So instead of allocating precious observational resources for incredibly improbable and incredibly infrequent transits, people just didn't even look. It was finally when planets such as these hot Jupiters were discovered via a different method, the radial velocity method, that people realized, maybe we should start looking for the transits. So after the first discovery of a hot Jupiter, which was back in 1988 or 1995, depending on how you want to count it, people got really excited about looking for transits. And this is a somewhat infamous figure from a conference in 2002. And what is showing here on the vertical axis is a prediction for number of transiting planets that would be found each month for each of 22 transit surveys that was going to go online in the year 2003. And to get some horizontal separation, they're shown as a function of the aperture size, the diameter of the telescope, ranging from a few centimeters to a meter, a few meters. And what I want you to notice here is that they range from about 1 transiting planet per month to a few per month, up to several tens per month, for a total of 191 transiting planets per month were supposed to be found back in 2003. This didn't end up happening. It turned out to be much harder to find transiting planets from the ground, or even from space, than people had anticipated. And I wasn't planning to go into why, but if people are curious, they could talk to me. Actually, Joshua Pepper is an expert in looking for transiting planets, and you can talk to him. I'm primarily a theorist and a modeler, but Joshua Pepper is an observer and an instrumentalist, so he could talk in even more detail than I can about this. So often when I give talks, I'll go to one of the online databases and take a snapshot of the number of known planets. Earlier this afternoon, I did that, took a snapshot, and this one, exoplanet.eu, has the count at 1,780. There are different online databases, exoplanets.org, exoplanet.eu. There's the Open Exoplanet catalog. and there are probably several others too. They'll have different counts ranging from 800 or so to several thousand. But the point is, we now know of a lot. And here's a plot of the discovery of exoplanets as a function of their mass. So planet mass, measured in units of Jupiter's mass, shown on a logarithmic scale here on the vertical axis, and year of discovery on the horizontal axis. And this blue dashed line here indicates the Earth's mass. And what you see is that there's this basically linear trend to the bottom of this envelope of points, heading downward on a log plot. So that means it's moving downward exponentially with time. And finally, it's starting to cross down below the Earth's mass. And so sub-Earth mass planets are finally being found. More than 1,000 total planets have been detected in the last 2 decades. None were known before 2 decades or so ago. And here's a figure that you probably... So this previous figure, those of you who are exoplanet enthusiasts have probably seen something like this before. Those of you who are exoplanet enthusiasts probably have not seen this figure, which I made fairly recently. And what this is showing is the minimum planet mass that had been found on at least a 1-year orbital period. Right? There's something interesting about planets that are sort of like the Earth, so that have 1-year orbital periods around sun-like stars, because those are the ones that might have surface temperatures that are conducive to life as we know it. So the minimum mass planet found on at least a 1-year orbit, measured in units of the Earth's mass now, so from 1 times the Earth's mass, 10, 100, 1,000, again as a function of year of discovery. So what you see is, interestingly, this is a record that has been set and broken only a total of 5 times. About 2 decades ago, a 2.5 Jupiter mass planet was found on a roughly year-long orbit. And then there were a few others. A decade ago, there was a 2 Saturn mass planet found on about a year-long orbit. And about 8 years ago, there was a 5 Earth mass planet found on about a year-long orbit. And so it looks like we got lucky early. It looks like we're overdue to find an Earth-sized planet on a year-long orbit. And with some luck, we might find one soon. What I would have said to you a year ago is that the instrument that might bring it to us is Kepler. Unfortunately, Kepler is broken. So Kepler is a space-based transit-detecting satellite. It stares, here's a picture of it, and its goal was to stare for its mission lifetime of 3.5 years at a single field on the sky, represented over here. And so these are all the different subfields here. There are many different cameras, each one looking at its own subfield. It's focusing on 150,000 stars, or it had been focusing on 150,000 stars in this field, and just staring, monitoring the brightness of each of these stars, looking for the slight periodic dips in the starlight seen when a planet would transit along the line of sight between us and the parent star. You might see this little smudge here. That shows you, for perspective, that's the full moon. So that's the size of the full moon in comparison to the size of the Kepler field. It's a really huge field on the sky. It's about 400 times the size of the full moon. Here's a summary of the planet candidates that Kepler has found. So what we're looking at here is planet radius, measured in units of the Earth's radius on the vertical axis, and orbital period, measured in days on the horizontal axis. And the color of each point indicates the temperature of the host star. So hotter looking colors, like the yellow ones and so on, are hotter stars. The cooler looking colors, the darker ones, dark purple and so on, are the cooler stars. Right here at the crosshairs is where an exact Earth analog, well, exact as a function of these 2 variables anyway, an exact Earth analog would be right there. So on a 1-year orbital period and the Earth's radius. And as you see, Kepler has not yet found an exact Earth analog. people were hoping that it would last beyond its nominal mission lifetime of 3.5 years. They were hoping that the mission would last for 5 or even 10 years, and it could just keep on staring at that field, build up better statistics, and find Earth-sized planets and sub-Earth-sized planets farther and farther out. It did last beyond its nominal mission lifetime of 3.5 years. It lasted for 4 years before it broke. But it didn't last as long as people had hoped. People are now trying to figure out what to do with it in its impaired state. And there was recently actually a call for proposals for what NASA should do with Kepler. And I ended up writing one of the proposals. And it looks like they're going to do something pretty similar to what I was suggesting, which is that it should, instead of staring at a single field, because it doesn't have the pointing precision anymore to point really precisely at one field, it should look at many different fields and cover a much bigger fraction of the sky and find as many hot Jupiters as it can. It's no longer good for finding Earth-sized planets, but it can still find hot Jupiters really well. So that's what I suggested. It looks like that's what it's going to do. Here's a figure that that Natalie Batalha from the Kepler team put together a few months ago, showing a really exciting announcement that Kepler made on February 26th of this year. So this here is showing the number of new planets found as a function of discovery year. The blue is showing those that are found by methods other than Kepler. The red is showing those that were found by Kepler. And then the yellow is showing the 700 planets that were found and announced on this one day, February 26th. So this was after Kepler had broken. It was just by virtue of using better analysis techniques to validate many of the candidates that I'm showing you here turned out to be real planets. And that's what's shown here. By the way, there's a lot of really interesting stuff going on here, which I should point out some of. So if you squint a little bit, you might see that there's a slight overdensity of points sort of in this vicinity. And it looks like there's more of a slight overdensity up at the larger radii than down here. You might or might not agree with what I'm saying here, but in the early days of looking for exoplanets, people didn't have access to all these planets here. They actually had found more planets than Kepler found in this region. And it looked like planets were found down to about 3 days and not inside of 3 days. And that was known as the 3-day pileup. And people wondered, there were papers written trying to explain the 3-day pileup. Now with the benefit of Kepler data, we see that the 3-day pileup doesn't look like a really real thing. They're planets with orbits much less than a single day. It does look like really large planets don't like to be found in orbits less than about 3 days. You find them, but there aren't that many. So that's still a kind of interesting problem. I have some ideas about why that's the case, which I could talk about later in the questions if you're interested. What else do you notice here?
Horizontal distribution slopes upward.
Horizontal distribution slopes upward. Good point. So one thing that you might notice before that even is just that there appears to be a pileup of planets down at about an Earth radius, or a few times the Earth's radius, right down here. And the reason that that's interesting is that, I mean, aside from the fact that, our planet is the Earth's radius, and so it means that planets like ours at least aren't super rare in comparison to other planets, is that these are the ones that cause the smallest dip in the starlight. So they're the hardest to see, and yet they're the ones that seem to be most numerous. Furthermore, farther out here, planets are less likely to transit just because the geometric probability goes down as the planet's orbit gets bigger. And yet there are many planets seen all the way out here. So what this indicates, when you do the statistics carefully, is that the planet frequency increases with decreasing planet radius and with the increasing distance from the star. As far as this slight upward trend in the slope goes, that's an interesting thing that you're noticing. It's not clear yet whether that is a real property of the population of exoplanets, or it could just be a selection effect. Because to see planets that are really small and in really long orbits is really tough. The reason that it's hard if they're in really long orbits is because you don't get many transits. So you don't get to build up as much statistics. I'm going to take you through the history of exoplanets in a sort of different way, again showing you mass versus orbital period. Mass measured in Jupiter's, tenth of Jupiter's mass. This is what the population of known planets looked like to astronomers back in 1995. I'm not including the one from 1988 because people didn't believe that one yet. So this was 51 Pegasi b. This was the first hot Jupiter found, the first exoplanet that everyone believed. It was in a short orbit, and it was almost Jupiter's size. And then these are the ones of our solar system. Via the radial velocity method, we've gotten now, over the last 2 decades, all of these gray points here. And what you can see is that it's hard to find RV planets that are small at large distances for similar reasons, not the same reason, but for similar reasons to with transits. The transiting planets are these red dots here, and these, a lot of the ones that have been found, so this is not just Kepler data, this is Kepler and the ground-based data. And those that have been found from the ground tend to be large, because it's really hard to find small planets from the ground. So that's why there are all these. And Kepler is starting to find some of the really distant ones out to a year or more. And then finally, out here, these blue points are so-called direct imaging planets. These are ones where they're far enough from their star that we can actually separate the planet's light from the starlight and get photons directly from the planet that way. The really interesting thing about the transiting ones and the direct imaging ones is that those are the planets for which we can get photons. We have a prayer of getting photons directly from the planet. These we definitely do, because that's how we find them. And these, for some of them, the brighter ones, we can also get photons directly from the planet. So how can we learn about planet structure and composition for transiting planets? We have 2 awesome times to learn about what the planets are made of and what their thermal structure is like. One is during what's called primary transit. So that's when the planet is transiting across the disk of the star. Here's a planet shown with an exaggerated radius, and the pink here is representing the planet's atmosphere. But the crucial thing is that the planet's atmosphere will be more or less opaque at different wavelengths of light, corresponding to molecules and elements that might be in the planet's atmosphere, which could have strong atomic or molecular features. By features, I mean bands or lines where they absorb light very strongly. So at the features where they absorb light very strongly, the atmosphere is more opaque and the planet is larger. It's larger in the sense that it blocks more of the starlight. Right? It's opaque out to a larger radius. At the other wavelengths, the planet is smaller. And so if we monitor the planet's apparent radius as a function of wavelength, we see that the radius varies by several percent. For hot Jupiters anyway, it can vary by several percent. And by doing that monitoring, we can start to learn what is there in the planet's atmosphere that's causing its radius to change this way. Then half an orbit later, the planet dips behind the star. Planet radius varies with wavelength. Secondary eclipse is when the planet dips behind the star. So immediately before secondary eclipse, we see the planet in the full moon phase. Immediately after, or during, we see the planet hidden by the star, so we don't see the planet. So we're getting the light of the star and the planet immediately before, and if we subtract from that the light from just the star, that gives us the light of just the planet. And if we bin this as a function of wavelength, we can get a spectrum of the light from the planet. And this is sensitive not just to the composition of the planet's atmosphere, but also to the thermal structure, what the temperature is as a function of height. And we've started to do these measurements for several tens of planets, somewhere between 20 and 30 or so. So different wavelengths correspond to different depths in the planet's atmosphere, and so by probing how hot the planet appears to be at different wavelengths, we're probing how hot it is at different depths. And I'll tell you about one project related to this that I worked on together with Dave Kipping, who's at the Center for Astrophysics at Harvard. This is an artist's conception of a planet that we were looking at called TRES-2 or TRES-2b. The artist, for some reason, included moons around the planet, which there's no reason to think that this planet actually does have moons, and there's some reason to think that it doesn't, because it's probably really hard for a hot Jupiter to maintain moons, but it looks nice in the art. And TRES-2 is one of 3 planets that were known in the Kepler field of view prior to the start of the Kepler mission. And so it's a planet that's been monitored an awful lot, both before Kepler, during Kepler, and with other instruments, including the ones that it was found with originally, which are some small ground-based telescopes looking in the optical. Kepler is looking in the optical part of the spectrum, and the Spitzer Space Telescope, which was an infrared space telescope looking in the near infrared part of the spectrum. And even in the near infrared means not that far beyond the visible. And even closer in the nearer infrared, it's been seen with some ground-based large telescopes. So Dave Kipping had the idea to look for the secondary eclipse of TRES-2 in the optical, in the Kepler data, to see if there was a difference in how bright the system was immediately before the planet dips behind the star and then while the planet is behind the star. And what he found was that it was too small a difference in brightness. He couldn't see a difference in brightness. But then he had a really clever thought, which was, instead of just using the several hours before secondary eclipse and then the several hours of secondary eclipse, why don't I use the entire orbit? Get way more photons. So what he did was he used the entire orbit, all the available Kepler data, and tried to fit a function to that data, a sinusoid function. And he was able to. By using all the orbit, he was able to get much better statistics and found that when the star plus the day side of the planet is visible, the system is 6 parts per million brighter than when just the star is visible. So the planet is contributing 6 parts per million of the total brightness. This is kind of amazing because it was actually 6 plus or minus 2 parts per million. Now Kepler was only designed to have a nominal precision of 10 parts per million. So by doing this, Dave Kipping and I were making a measurement that was 5 times more precise than Kepler was originally designed to be able to do. It's, I believe, still the most precise brightness measurement that's ever been done of an exoplanet's optical brightness. And so we wrote it up, and it got some attention. It was there's a kind of fun article written in Time about it. It was called "The Blackest Planet in the Universe." So why was it called the blackest planet in the universe? Well, so it's really dim, and if you interpret this 6 parts per million as due to reflected light, then that would mean that the planet's reflecting about 2% of the light that hits it. However, I took all the available data, not just the Kepler data, but the infrared data that had been seen from the ground, the infrared data that had been taken with the Spitzer Space Telescope, and I tried to put together atmosphere models that would consistently explain all of the available data. And what I found was that in the models that are consistent with the data, it's true that we get an amount of light back that is sort of consistent with the planet reflecting 2% of the light. When we actually look in the model and see where that 2% comes from, it turns out that 95% of the photons we get are thermally emitted. And only 5% of the photons we get are reflected. So what that means is that you take 5% of 2%, that brings you down to 0.1% of the light that hits this planet is being reflected, which is amazingly black in the sense of non-reflective. For comparison, black paint reflects about 4% of the light that hits it. The blackest materials you can think of on Earth, charcoal, coal, paint, They all reflect about 4% of the light. This planet reflects about 0.1%. So the reason that we're seeing it isn't the reflected light. The reason we're seeing it is that it's glowing. It's glowing a kind of deep red color like the coils on an electric stove, just by virtue of being hot. Although, so blackest is actually a very good term because black means non-reflective. Some of the things that were written about it said that it was the darkest planet in the universe, which is incorrect for several reasons. For one, lots of hot Jupiters are probably comparably non-reflective. But for another, it's actually not that dark. It's really hard to see because it's right next to a really bright star. But if it were in our solar system, it would be about 3,000 times brighter than Venus, which is the brightest planet from our perspective. It's just that it's really far away, and so it looks faint to us. Another way of putting that is that if Venus were in this system, we wouldn't have had a prayer of getting any optical light from it because it would have been 3,000 times dimmer. It was also actually briefly, the top news story on Yahoo News, which was like really weird to me. This should never have been the top news story on Yahoo News. But anyway, it's kind of fun that it got the attention. So the habitable zone. I'm going to switch gears a little bit to talk about habitability in the universe. So this is the figure that every astronomer who talks about the habitable zone is contractually obligated to show. What it's showing here is the mass of a star on the vertical axis measured in units of the sun's mass. So this is the sun, a tenth of the sun's mass, 1/100th, 1/1000th. This is distance from the star measured in astronomical units. So this is the Earth's distance from the star, a tenth, 1/100th, 1/1000th, 10 times the Earth's distance, 10 AU. And this ribbon here is showing, according to a calculation made by Jim Casting and collaborators back in 1993, this is the region that corresponds to surface temperatures that are appropriate for liquid water, the so-called habitable zone. This is a wonderful paper. One of the important things it did was it pointed out how strongly the habitability depends on properties of the star. The mass is a proxy for brightness, so more massive stars are brighter, and so the habitable zone moves farther out. It stays about constant width in these logarithmic units, but in physical units, it gets wider as you move up here, and therefore you move out there. So this is a great advance, but what it leaves out is how habitability might depend on planet properties as well. So this is something that I've worked on with, at the time she was a really talented undergraduate at Princeton named Courtney Dressing. She's now a really talented graduate student at the Center for Astrophysics at Harvard. And we looked at how these various properties of a planet can affect the habitability. So how fast is the planet spinning? What's the distribution of land and ocean? What's the atmosphere made of? That's a really crucial part of determining planetary habitability. The obliquity, or the tilt of the spin axis, right? That's what gives the Earth its seasons. The fact that our spin axis is tilted relative to the orbital plane by about 23.5 degrees. The eccentricity of the orbit. The Earth's orbital eccentricity is very low, and it varies between about 0 and about 0.06. Right now it's about 0.02. And there are these cycles called Milankovitch cycles, which cause the Earth's eccentricity to vary on timescales of 100,000 to 400,000 years. Well, in exoplanetary systems, the eccentricity could vary a lot more. The distribution of eccentricities in exoplanet systems extends way higher than eccentricities in our solar system. Right? Pluto is the super eccentric planet in our solar system. It's not even a planet, right? But it's the super eccentric body in our solar system. And its eccentricity is only about 0.25. Whereas in exoplanetary systems, there are planets, many planets known with eccentricities bigger than 0.5, going all the way up to 0.93 or even 0.97. And a long-term history of climate. Right? There can be so-called hysteresis effects. In other words, you hold everything else the same, but you start off with a low temperature, you get a different present climate than if you hold everything the same but start off with a high temperature. One example of this is a so-called snowball Earth state. And it's thought that the Earth has been through several snowball states in the last billion years. The idea of this is that if for some reason the Earth freezes over, then it becomes very shiny because snow and ice are very highly reflective, and it doesn't absorb much light from the sun because it's reflecting it all back out to space. In a state like that, you can have everything else the same, atmospheric composition, obliquity, eccentricity, all these things, and yet the planet will have a really low temperature instead of the moderate temperature that we have now. And it's really hard for a planet to melt out of a so-called snowball state. The Earth, if it ever did go through a snowball state, and most geologists think it did, obviously did melt out, but that probably was a really difficult process. Now, again, sort of a philosophical point here is that the real habitable zone, in my view, this is sort of a cartoon to be illustrative. The real habitable zone is a cloudy region in a multidimensional space that characterizes planets and their stars. One of these dimensions is distance from the star. So the way that the habitable zone is always talked about is it's a range of distances, right? But the casting plot shows that, well, it's not just a range of distances, it's a range of distances if you assume a star. So you have to specify the star, but you have to specify all these other things too. And so to get an R in and an R out, you need to specify a trajectory through this cloud. What people typically do is they hold the planet's properties very close to the Earth's. But they don't have to be so close to the Earth. And if you pick a different trajectory, you'll get a different R in and R out. So why do people think about the habitable zone this way? Well, the reason is that distance from the star is basically the most easily observable of all these properties. It's really hard. Eccentricity is moderately observable. Obliquity is really hard to observe. Atmospheric composition is super hard to observe. So if you want something that's based on an observable, you want to talk about distance from the star. But the important thing to keep in mind is that anytime someone shows you where the habitable zone is, that's not where the habitable zone really is. Right? That's making an assumption of all the other properties of the planet. And if you vary those properties, if you change the atmospheric composition, you change the obliquity, you change the eccentricity, you change how much land versus ocean there is, you change all these things, you'll change where the habitable zone is. And so if someone tells you, for example, NASA with the Kepler mission has been very fond of saying, we finally found a planet in the habitable zone. Well, okay, I mean, it might be, just because it's in what is called the habitable zone doesn't mean that it has surface conditions that are conducive to liquid water. And there are planets that are not in the nominal habitable zone that might have surface conditions good for liquid water. A summary of exoplanet knowledge here is, this is a subset of exoplanet knowledge, is that there's several hundred billion stars in our galaxy, and we now know that to within a factor of a few, there's about one planet per star. There might be one planet every 3 stars, there might be 3 planets per star, but on average, something like a planet per star. So there are hundreds of billions of planets in our galaxy. And it looks like there's between something like 1/100th and about 1 so-called habitable planets per star, where I know I was just criticizing the idea of habitable, but what I mean here is falling in something like the classical Jim Casting 93 habitable zone. Planets that have a reasonable shot of having surface liquid water. And so it seems that there are probably billions of habitable, I'm going to sound like Carl Sagan, there are billions of habitable planets in the Milky Way galaxy. But how many inhabitants? So why did I put a picture of a deer here? So this is actually a picture of a deer on the Institute for Advanced Study campus. And the reason I put this here is, suppose you wanted to know how often there's a deer visible outside a window. What fraction of the time? So there are many things you could do to try to approach it. One thing you could do that would not be insane would be to just say, okay, I'm going to go sit by the window and wait how long I have to wait until the first deer comes into sight. And that'll give me some measure. It won't be a perfect measure, but it'll give me something. So if you do this in New York City, probably have to wait a really long time. It might actually not. So I grew up in Boston, and one day when I was growing up, there was a moose that ran down Beacon Street. So it actually might not be like an infinite amount of time in New York, but it would be a really long time, right? So if you're at the Institute for Advanced Study in Princeton, or like in a lot of places in Pennsylvania, New Jersey, and so on, you might have to wait a few hours. You wouldn't have to wait that long. And so you could rightly conclude from doing that experiment that deer are probably visible outside the window at the IAS in Princeton way more often than they're visible outside the window in New York City. So I'm just trying to motivate this as a reasonable way of approaching a question of how long on average does it take something to happen. So now we're going to take a look at how long it took life to show up here on Earth, right? Because we can't do a sort of systematic study of having many, many people sit by, right? With deer and windows we could, but with life on planets we can't, because we only have one example. So I'm not a geologist, but this is my cartoon understanding of a timeline of the Earth's history. The Earth formed 4.5 billion years ago. The present is down there. The Earth became habitable something like 3.9 billion years ago. What I mean by this is that the rate of impacts that were probably sterilizing had decreased to the point that probably from about 3.9 billion years ago to the present, the Earth has been continuously habitable. And there's evidence that life had begun by about 3.7 billion years ago. Not everyone agrees with this. Basically, everyone involved in origin of life studies agrees that there was life by 3.2 billion years ago. Most people agree that by 3.5 billion years ago there was life. And an optimistic but not crazy reading of the data suggests that by 3.7 billion years ago there was life. For the purpose of this discussion, I'm going to assume that there was life by 3.7, although it might not be true. If it's true, then probably life didn't show up at 3.7, because the first evidence that we have is probably not the first life, right? It probably took some time for life to build up to the point that it could leave evidence that we would find 3.7 billion years later. So that would mean that sometime in that 200 million year window, life showed up. So that's how long we had to sit by the window waiting for life to show up. And there's a standard argument in the origin of life community that the fact that this is fairly short means that life is probably common. So down here, intelligence shows up something like 100,000 years ago, where by intelligence I mean creatures that are capable of wondering about the frequency of life in the universe. They might not have had a word for life in the universe back 100,000 years ago, but they were basically like us and they could have thought about it. So the argument, right, goes life arose early, so abiogenesis, that's the process of life coming from abiotic conditions, is probably a probable process. And some people take this argument really seriously. But how probable is it? So together with Ed Turner at Princeton University, I put together a proper statistical analysis of this argument. And the way our argument goes is as follows. First, we say the argument on the previous slide is basically right, that the early emergence of life on Earth does give us some confidence that abiogenesis is a probable process. However, even if life is rare throughout the universe, still it's not surprising that life arose early on the planet that we happen to find ourselves on, because there's a severe selection effect here. We are here, especially if evolution requires perhaps billions of years to develop intelligence. For example, there's got to be some minimum evolutionary time scale to go from the simplest life to creatures that can think about abiogenesis, right? It can't happen in a minute. Probably can't happen in a decade. Probably can't happen in 100 years. If the minimum evolutionary time scale is 3.5 billion years, then it would be impossible for us to find ourselves on a planet with late abiogenesis, even if life is very rare in the universe, and abiogenesis is very improbable. However, finding life somewhere that we didn't have to find it would count far more towards the conclusion that life is common in the universe. So what do I mean by this? Somewhere we didn't have to. Well, there are three possibilities I suggested. One is so-called shadow life here on Earth. That would be life that we'd find on Earth that we would be confident had a different evolutionary origin. For example, if we found life on Earth that wasn't based on DNA or RNA. And there might be other ways also of knowing that it had a different evolutionary origin. Or finding life elsewhere in the solar system, on Mars, on Europa, or Ganymede, if we were confident that there was no panspermia in either direction, right? Neither Earth seeded the other body, nor the other body seeded the Earth with life. Or if we were to find life on an exoplanet. So to give you a flavor for how I did this statistical analysis, I want to introduce a few equations, but they're pretty easy. And this is to introduce you to Bayes' theorem, which is a really important idea in modern statistics. So the way it goes is if A and B are any two, I say possible, but really I mean probabilistic events, any two events to which a probability can be assigned, then the probability that A and B both happen is the probability that A happens, this vertical line means given that B happens, times the probability that B happens. But of course, and conjunction is commutative, so I could also say it's the probability that B happens given that A happens times the probability of A. Well, two things that are equal to the same thing are equal to each other. So we set this up, we divide both sides by the probability of B, and we get this boxed equation here, which is what's called Bayes' theorem. Now, Bayes' theorem, written with A's and B's, isn't very illuminating, but it's more illuminating if we replace A with M for a model or a hypothesis, and B with D for some data. And we get that the probability that a model is true, given some data that we take, is equal to the probability of the data assuming the model, times, now I'm giving this helpful subscript, the prior probability of the model, and then divided by this normalization factor. And the terms in Bayesian statistics for these terms, the words for these terms are, this is called the prior, this is called the posterior, so prior is before we look at the data, this is the posterior after we look at the data, and there's another term that, this here is called the likelihood function. You might hear people talk about the likelihood sometimes. So we're going to return to the quiz. The test for the disease, 99% sensitive, 99% specific. How nervous should you be with a positive result? Many medical doctors, there might be some medical doctors in this room, and I'm sure you're not among the ones who would say, many medical doctors would say, the probability that the patient is sick is 99%. But that's, of course, wrong, because it's a trick question. I didn't give you enough information. You need to know the prior probability of having the disease, which is the population incidence of the disease. Right? The probability of being sick given a positive result is the probability of positive given sick, which is 99%, times the prior probability of being sick. For example, if it's a test for feline leukemia, it could be a super accurate test for feline leukemia, but if it comes back positive, it's a false positive because people don't get feline leukemia. So if the prior is 0, then the posterior is 0, no matter how large the likelihood is. So one other example that I like to give to show that it's sometimes represented as though some people are so-called frequentist statisticians and some people are Bayesian statisticians. If you haven't heard of those terms before, don't worry about it. If you have heard of those terms, I'd just like to make clear that everyone is actually, there isn't any real controversy. I mean, there's some sort of controversy in that people argue with each other, but everyone is actually a Bayesian. For example, if I were to tell you that the way that I got here tonight is I drove my 2002 Corolla, you would probably believe me, because I have an honest-looking face. If I were to tell you that the way I got here tonight is that I rode on the back of a fire-breathing dragon, you would probably not believe me, even though the information that you have is the same, right? I said so. That's all you have. But you have a strong prior against people riding dragons to get to amateur astronomy meetings, right? So the upshot of a Bayesian analysis of our single datum being that life showed up sometime in the first 200 million years after the Earth became habitable, and that intelligent life showed up 3.5 billion years after that, roughly. The upshot is that you might not be shocked by this because we only have one data point, but there's not enough data yet to say how probable abiogenesis is. But this is a point that's important to make because a lot of researchers working in origin of life don't appreciate this. In fact, there had been several papers before that had not done a proper Bayesian analysis, and it concluded that the probability that abiogenesis is very improbable is almost zero. They said that there's a 95% probability that life will show up within 1 billion years given early Earth-like conditions. And what I found when taking a Bayesian analysis of what they had done in that argument, they didn't write a Bayesian statistics paper, but when I tried to reinterpret what they had done in a Bayesian sense, I realized that that 95% confidence that they were getting was entirely because of a hidden prior that they were using. It had nothing to do with the data. If they had entirely ignored the data, they still would have gotten 95% confidence that life would show up within 1 billion years just because of the shape of their prior. And that's what's important about Bayesian statistics, is it shows you the relative importance of prior and data. In coming years, we might have evidence of life with an independent origin, as I was mentioning a moment ago. Well, first of all, it would be like the most exciting discovery in the history of mankind. And also, it would dramatically change our conclusions, right? It would mean that not only is there that one other inhabited planet, but there must be lots of others. Right? I haven't shown you this, but I'm telling you, the upshot of the Bayesian analysis is that if we found even a single example of another planet that had life on it, that would basically rule out the possibility that abiogenesis is very, very improbable. But that is totally still a possibility right now, because we had to be on a planet where there was life, and we might have had to be on a planet where life showed up really early.
Does that make panspermia more viable?
How do you mean?
The thought theory you're describing there, okay, doesn't exist because of the habitual part of the planet and the habitat, right, of another system, right? You have no planet there with life on it, or you're not sure that there is, and it completely exonerates that theory. Then does not panspermia then weigh more heavily in the hypothesis?
Well, so you're saying if we were to find life on a planet around another star?
No, that life from another star arrived here because of the evolution in Milky Way or in the rest of the universe, for that matter.
So it's certainly true that if there's a lot of life in the universe, then the chances that life on a planet around one star might end up spreading to a planet around another star is higher, because if there's one dandelion, you get way fewer seeds than if there's a whole field full of dandelions. That's certainly true. However, it looks like, so panspermia within a solar system is probably not super difficult. Panspermia from one solar system to another is probably really hard. It might happen once in a while, but it's probably really hard.
Spiegel?
Yes?
Is there any evidence that would support exoplanet inside the transit across the star, and like, say, for instance, the wobble of a star as it moves through space?
Sure, yeah. So I was mentioning the several main methods that have been used to discover exoplanets. So one is the transit. One is the radial velocity method. And I didn't talk about what that is, but the way that works is you tend to think of stars as sitting still and planets as orbiting around them. But actually, planets are not massless. They have mass. And so they tug on the star at the same time as the star is tugging on them. And so what actually happens is that the planet and the star both orbit their mutual center of mass. And so the star is moving a little bit if there's a planet around it. That means that sometimes the star is moving towards us and sometimes it's moving away from us. When it's moving towards us, its light is a little bit blue shifted. When it moves away, the light is a little red shifted. When we look, we see that a lot of stars have this periodic change from slightly red shifted to slightly blue shifted light. It's called the Doppler shift, the Doppler effect. And the only thing we can think of that would cause this periodic change from red shift to blue shift and back again is the presence of an unseen companion. If the companion is in the planet mass range, so ranging from sort of like the Earth's mass or something a little less to maybe 10 or 20 times Jupiter's mass, then we call it a planet. Yes?
Would you say that the Earth and the Moon revolve around a common center of gravity, or does one revolve around the Earth?
They come pretty close. So they're both in orbit around the Sun. But if you switch to a frame of reference that is centered on the center of mass of the Earth-Moon system, so that frame of reference then is like we take a camera and we put it above the solar system, and we have the camera move along with the center of mass of the Earth-Moon system. What that camera would see is the Earth and the Moon both orbiting around the common center of mass of the Earth-Moon system. An interesting thing.
Mass is inside the sphere of the Earth.
That's exactly right. It's about 2/3 of the way from the center of the Earth to the surface. So the Earth isn't moving all that much in that frame, but it is moving a bit. So I'm looking at the time now, and I was going to tell you something about what happens when stars grow up and die, what happens to planetary systems around them, but my talk is running a little long, so maybe I should wrap up now. So thank you very much.
Could you go back to one of your earlier, that slide where you called your cartoon of your timeline?
Sure.
Of life? That one. Like, it did not take very long at all for life to begin on Earth, but that's microbial life.
That's right.
It took a long time for complex life to show up.
That's right.
That didn't show up till, what, 1 billion years down here.
Something like that. That's right.
When I say complex life, I mean even a grass,
Sure.
So the probability that microbial life exists in the universe is probably pretty large, but complex life might be very rare because it's, in our case, at least for our system, complex life took a long time to develop.
So I'm with you that the probability of complex life or the frequency of complex life is probably significantly lower than the frequency of microbial life.
Yeah.
But one of my points here is that what you said at the beginning, that microbial life is probably common in the universe, might or might not be true. We just don't have evidence to say one way or the other at this point. I hope you're right.
We only have one case that we're looking at.
Right. I hope you're right, but it might not be true.
So it'd be real exciting to find real life on Mars.
Yeah, it would. Yes?
Does the Drake equation fit into this model at all?
Well, this is sort of more an input to the Drake equation. So, one of the terms in the Drake equation, is anyone here not familiar with the Drake equation? Okay, so the Drake equation is, Francis Drake, an astronomer, wrote down an estimate of the number of intelligent civilizations in the Milky Way galaxy. And it was a product of a bunch of terms. So one term was the star formation rate of the galaxy, how often stars are being made. There are a few terms that end up giving you basically the number of planetary systems, and then there's the fraction of planetary systems that have habitable planets, and the fraction of those where life arises, and the fraction of those where intelligent life arises. This is trying to constrain one of those terms, which is the fraction of habitable planets on which life arises. Now, when Carl Sagan and Drake and various other people who are real optimists about the possibility of life in the universe try to put in some numbers in the Drake equation, they tend to put in numbers like 1 for the probability of life arising given habitable conditions, or 0.1, or maybe 0.01. But these are all numbers that are like pretty big, right? If there are billions of habitable planets in our galaxy, then if you say life shows up on 1 out of every 100 of them, that's still giving you, tens of millions of inhabited planets. However, when I've spoken to people who work in origins of life research, and I've said to them, forget everything on this cartoon, right? Pretend you didn't know. So these are biochemists. And I say, pretend you didn't know anything about when life actually showed up on Earth. Pretend all you knew was what you know about biochemistry. What would you estimate is the probability, given early Earth-like conditions, that life would show up within 1 billion years? And I've gotten answers that range from 95% on one end to 10 to the minus 70. And this is from highly, in fact, the person who said 10 to the minus 70 is one of the most highly respected people in origins of life research. And if that person is right, then we are probably alone in our observable universe. Sorry, not an optimist? Well, it's based on the fact that it looks like, from chemical studies, it looks like it might be really hard to get protobiology going. Now, this person was not super confident that 10 to the minus 70 is the right answer. He's just saying that's his best guess. But if it ended up being, 5% or 95%, it wouldn't knock him dead. He wouldn't be shocked. His best guess is 10 to the minus 70. So there might be lots of microbial life in the universe, or there might not be. Yes?
I read Cosmos by Carl Sagan, and there was an experiment that was conducted where he contained a mixture of very simple gases like methane and hydrogen sulfide, and they ran electric currents through as lightning bolts through the primordial atmosphere in the earlier stages of life on Earth. And it developed a primordial spook. The molecules became more complex. I don't really think they achieved a protein status, but the basic idea was that given what we know about life at the beginning, these sort of things possibly happen. That
Sure.
starting point for life here on Earth.
Yeah, so we this type of experiment is often referred to as a Miller-Urey experiment. Stanley Miller and his advisor, forget the first name, but Urey. Harold Urey. Together made this sort of experiment where, as you said, there were some gases that were probably around on the early Earth, and they zapped it with electricity and did this for a while, and then looked at what they got. And they got various kinds of organic sludge, and there were amino acids, which was exciting, and even some small chains of amino acids. The case for being pessimistic, and I'm not trying to convince you to be pessimistic, I'm just trying to convince you that there is a reasonable case for being, pessimistic is the wrong word, for thinking that there's a reasonable case to be made that it's really hard to get life started. And the way that case would go is that, so we don't know how long the minimum length so-called word, if you think about having letters, which are amino acids that can be strung together in different orders, or that are nucleotide bases to make DNA or RNA chains of a certain length, right? People don't know if life got started by proteins first, or by DNA first, or RNA first. If it's DNA or RNA, the alphabet is 4 letters. If it's proteins, the alphabet is somewhere between 20 and 500 or so letters. There are 20-ish common biologically useful amino acids, but actually there are more than 500 total amino acids. And we don't know how long the minimum length word made from any of these compounds is. What I mean by minimum length word is the minimum length chain that can self-replicate, and do so not perfectly, because You want it to be robust in its self-replication, but also capable of making errors so that it can participate in Darwinian evolution. Right? If it were too robust, if it made an exact copy of itself every time and never made a mistake, then that also wouldn't be proto-biological. We don't know what the minimum length word is. We also don't know how dense the set of words is in the space of all possible chains. Right? It might be, for example, that for chains that are up to 150 nucleotides long, none of them count as protobiology. And once you hit 150, there's one needle in the haystack. Right? You need to hit exactly the right chain that's 150 long. And if you don't hit that, you have no chance of getting life started. If that's the case, then we are almost certainly alone in our observable universe. However, it might be that you can get by with a chain that's only 80 long. Or it might be that you get up to 150, and there's not just one, but there's 4 to the 148 of them. It might be that almost any chain that's 150 long counts as protobiology. We just don't know. But there's one more thing that adds to the case for thinking that life might be rare, and that is that, so people often talk about you need to get catalytic function going. You need to have molecules that do something. But the problem is, and I was talking about this just recently with a biochemist, the problem is that you don't just want the molecules to do anything. Like you want them to be so-called autocatalytic. You want them to make themselves. But the kind of catalytic function that you tend to get most easily is destructive. So if you start getting short chains of RNA, what they tend to do is go around chopping apart longer chains of RNA and making it hard to develop these long words that might ultimately be necessary for getting life started. So this is not a proof by any stretch. There might be lots of ways that I'm not describing here to get life going much more easily than the way I'm making it sound. But there is a case for thinking that life might be very rare. Yes?
Isn't the concept of self-organization, doesn't that enter into the possible length of the word? And if it would self-organize, it might make it a lot shorter.
Sure. We just don't know how long the minimum length word that can participate in autocatalysis is.
Do you think this pessimism is unfashionable or unpopular because it's like fuel of creationist side of the argument?
Yeah, well, so when I wrote this paper, so the paper was not arguing that life is rare. It was simply arguing that the evidence from early life on Earth is compatible with life being rare in the universe. Certainly was not arguing that it was even compatible with life being unique to Earth, just that it's possible that life is rare. However, there were several creationist blogs that noticed our paper and really seemed to like it. Like somehow, even just having life be rare seemed, I guess, better to them than having life be common, even if we're not the only ones. Yeah. For most astronomers, it's depressing if we're the only life in the observable universe. But it's a real possibility. But I'm certainly not claiming that I've shown that that's the case. I hope it's not.
I believe his name was Whitmore, who said, creating a universe is easy, all you need is matter.
Yep. Yes?
What were the conclusions from the LHC, the Hadron Collider over in Switzerland?
Oh, that's beyond my expertise. Thanks, though. Okay, thank you very much.